Now, before I go on, are there any challenges or questions or even contributions that anyone has with respect to what we have done so far? Okay, so one of you sent me a message on WhatsApp asking me a question on operating system, and I have responded. I hope the response was okay. Like that, if anyone has any challenge across the week, any time in the week, and you feel you want clarification, you can also send me a message on WhatsApp. When I get it, I will respond. All right, let's look at the outline for, excuse me, the outline for today's lecture. We're going to introduce the processor, a few tips. Then we look at the scheduling policies of the operating system. And we look at how the processes are scheduled. There are some algorithms that are followed during the scheduling of processes. We will summarize and conclude as usual. These objectives, after completing this chapter, you should be able to describe the difference between job scheduling and process scheduling and how they actually work or operate or relate. We look at the disadvantages and disadvantages of process scheduling algorithms that are preemptive versus those that are non-preemptive. Then we look at goals of process scheduling policies in single core CPUs, 6 different process scheduling algorithms, and the role of internal interrupts and the tasks that are performed by the interrupt. All right. Now, recall that last week we differentiated among 2 instructions or processes. We talked about the IO-bound processes and the CPU-bound process. We said that the IO-bound instructions were those that were keen, always performing input-output operations, and the CPU-bound were those that were, that are always performing CPU computations. This is a simple C program to demonstrate what we mean when we say IO and CPU. This program, there are 3 sessions. The first session, which is an IO session or cycle, is simply some printf statement that is displaying text on the screen, and scanf that is accepting input from the keyboard. So these are what we mean when we say input-output operation. These are just examples, okay? Then if you look at the third session also, it is an IO cycle, further printf statement. These are statements that are displaying stuff on the screen. Then when we talk about CPU cycle, this is where actual computation, takes place. You look at this, adding A to B and assigning it to C, subtracting C from the product of A and B, subtracting B from A and assigning it to E, dividing D by E and assigning the results to F. These are what we refer to when we talk about CPU cycle. These are just a few of the CPU, bound instructions that we have always been talking about. Notice we also talked about the long-term scheduler, the short-term scheduler, and the middle-term scheduler. We also talked about the process control block. So these are things that we have already looked at in our previous lessons, and we are going to continue, and these are going to come into our classes today. So when we say the processor manager, this is the one responsible for allocating the processor or the CPU to execute a job. Okay, so I always say that a CPU is given to a process, then the process takes over the CPU. When I mention that it is the processor manager that is actually the one that allocates the CPU to a job. Okay. Now, after a job has been placed on the ready queue, that is, after a job has been brought to the ready queue in the main memory, the process scheduler takes over. You know, it is the job scheduler that brings the job from the job queue to the ready queue. Okay. When that is done, this process scheduler takes over the rest of the computation. Now, in any operating system, there are some policies that the scheduling process must adhere to. Remember, in our previous class, one of our previous classes, we've talked about policies. Okay. Now, in a multi-programming environment, because there are usually more jobs to be executed than there are in terms of numbers of the CPU, there is the need for the operating system to schedule these jobs in order to address three limitations of the system. Now, every computer system has a finite number of resources. When we talk about resources, we're talking about the disk drives, the printers, the tape drives, etc. These are finite, okay? They are not in abundance. And so there is the need for the operating system to schedule the usage of these finite resources. The second limitation is that some of the resources are not reusable, okay? Or some of the resources are not shareable. Once they are allocated to a process or a job, it cannot be shared by any other process. Example is a printer. When a document is being printed, when one process is using the printer, no other process can use the printer concurrently. That is a limitation. The third limitation is that some of the resources cannot be automatically reassigned. Okay? If you take a tape drive or even a memory location, when a process occupies a memory location and that process completes its execution, that memory location cannot be automatically reassigned. The operating system has to come in to do the reassignment. Because of these three limitations, the operating system has to schedule these jobs in order for the resources to be used in an efficient manner. Otherwise, without the intervention of the operating system, one process will take over a resource and it will not release it for others to use, to monopolize the limited resources on the computer system. Hence, the need for scheduling. Now, there are some policies that every good scheduling must comply with. These are some of the policies. The first one is that every good scheduling process or every good scheduling process scheduling must maximize the output, the throughput. When we say throughput, we are talking about how much work can be done. Okay, every good process scheduling must maximize the throughput. 2, minimize the response time. That is how long it takes for a process to return to the user, for the user to be able to access or use the process. Also, to minimize the turnaround time. The turnaround time, we are going to look at this into detail. That is how much time it takes to complete all the jobs in the CPU or on the main memory. Also, to minimize the waiting time, how much time a process waits in order to gain access to the CPU. To maximize the CPU efficiency, how do you, schedule the CPU so that even though it is limited, it can execute as many processes as possible. And also to ensure fairness for all jobs, to ensure that a job does not wait forever in the queue. Like you go to the hospital and there is a queue, you join the queue. You know that when an ambulance arrives, the doctors will have to leave the queue, those who are not in an emergency situation, and attend to those in the emergency situation. How do you schedule this process such that if the whole day emergency situations are coming, what will happen to those on the queue? So a good process scheduling must always take into consideration these 6 policies that we have mentioned here. Now, the final decision rests with the system designer. Whoever is designing the system will have to decide which of these policies is of utmost importance to them, and then they will focus on that. If you go to the hospital, like the scenario I have just created, is the hospital interested in the normal patients, or is it so keen on seeing to people with emergency? If that is the case, then those in the normal queue can wait for the rest of their lives. But if the hospital is interested in taking care of, the general well-being of clients, then they must find a way of balancing the two. So the final decision rests with the system designer, who must determine which criteria are most important for the system that they are designing. Now, before we start with the scheduling algorithms, let's take note of this preemptive and non-preemptive scheduling. Now, the process scheduler often uses a timing mechanism. I am sure I have always talked about this CPU timeline here. And the process scheduler, what it does is that it uses a timing mechanism. That means it divides the CPU time into it divides the CPU over time. So let's assume it selects every second. So at time 0, time 1, time 2, time 3, etc. So what it does is that the operating system or the process scheduler will periodically interrupt. So here we have selected 1 second. So it means that after every second, the process scheduler will interrupt. It will come into the room. So assuming there's a doctor in the room, this process scheduler, let's assume, is the secretary. After every 1 second, the secretary will come into the doctor's consulting room. That is, he will come to interrupt the operation of the doctor, okay? And when the secretary interrupts, the secretary can decide to tell the doctor to stop working on that patient and bring in a new patient, or the secretary can determine to tell the doctor to go on, okay? The same thing happens in the computer system. The process scheduler periodically interrupts the running processes at a predetermined time. Now, when that time comes, the scheduler suspends the current running job, reschedules it into the ready queue. So that is what happens in an interactive system. So here at time 0, operating system, the CPU will be working on process A. Okay, and when the process scheduler interrupts, it will take process A from the CPU and brings in process B, whether A has completed or not. Then at time 2, it will bring in process A again, assuming these are the only 2 processes on the system. Okay, so the process scheduler will be interleaving these jobs until they have completed their execution. Okay, so when the process scheduler suspends, the CPU is now allocated to another job that runs until the next timer goes off. The job will, or sometimes when the job issues an IO, then there is no need for the process scheduler to bring the job back to the CPU because it is waiting on an input-output operation or until the job has finished its execution. Now, let's come to the preemptive and non-preemptive. A scheduling strategy that interrupts the process of a job and transfers the CPU to another job is called preemptive scheduling. So this scenario that I have painted here, where even though A has not completed its execution, when the timer goes off, B is brought into the CPU. When you have this form of scheduling, okay, it is called preemptive scheduling. Even though A is not completed, process A is preempted and B is brought in. When the next timer goes off, even though B is not completed, the B is preempted and A is brought in. That is preemptive scheduling. Now, opposite to that is the non-preemptive scheduling, where when A has not completed its execution, the process scheduler will continue to execute it. So A will be here, the next timer, A will be there, the next timer, A will be there until A has completed its execution. Then B will be brought into the system. Next timer, B will be there until B has completed its execution. This type of scheduling is called the non-preemptive. Here, once a job captures the processor and begins its execution, it remains in the running state uninterrupted until it issues an IO request or it is finished. So in the event that A issues an IO request, then the A can be brought out of the processor because it can no longer execute. So this one is natural suspension of the process A, and then B will be brought in. Okay, so this is the non-preemptive scheduling. Are you all with me on this?
Yes, sir.
Yes, sir.
Very good.
Yes,
Now,
sir.
good. With this understanding, let's look at the scheduling algorithms. So the process scheduler relies on some algorithms to allocate jobs to the CPU. We are going to discuss 6 of these algorithms that have been widely used. We will look at the first come, first serve. We will look at the shortest job next. We will look at priority scheduling. We will look at shortest remaining time. We will look at shortest remaining time. Then we will look at the round robin and the multiple level queues. Okay, let's start. The first one, first come, first serve. This is the queue you join when you are going to buy wache at that wache joint when you go to your campuses. Okay, this type of scheduling is a non-preemptive scheduling algorithm. That means that once a job takes over the CPU, it will be there until it has completed or it executes a natural wait. Okay. This is done based on their arrival time. So if process A comes before process B, B will wait. Okay. It is a very simple algorithm that implements the FIFO, that is the first in, first out queue. This type of algorithm is optimal or is best suited for most of the batch systems. You know, the batch systems where processes or instructions are put together in a file and the file is run as a batch. This first come, first serve algorithm is optimal for these batch systems, but it's not acceptable for interactive systems. Because in an interactive system, you want to access or you want to serve many users as possible, okay, at a given time. And so if one person comes and the person is buying 5 of the wache, everyone will have to wait. The person will buy first one pack, second one pack, third one pack. That thing is sometimes quite annoying and it is not acceptable for interactive systems, okay? As new jobs enter the system, their PCB is linked to the end of the ready queue. I'm sure by now you are conversant with the PCB, that is the process control block. In a typical first come, first serve system, there are no wait queues. Each job is run to their completion. What is the wait queue here? There's no IO wait, okay? The job is run to completion. So once you start, you finish your work. There is no wait. There's no time your process will be in the wait queue. Okay. Once it moves from the ready queue, it goes straight to the CPU. And because you have the whole time to execute, you don't need any wait queue. Okay. All right. Now let's look at the turnaround time. What is the turnaround time? The turnaround time is the time it takes for the CPU to execute all the jobs in the ready queue. Excuse me. If you look at the current situation that we have on my screen, there are 3 jobs, A, B, C. The turnaround time, or the average turnaround time, is the average time it takes for the CPU to execute all the 3 jobs. So there are 3 jobs. Job A has 15 CPU cycles. Job B has 2 CPU cycles. Job C has 1 CPU cycle. That means when the CPU executes, the timeline that I always draw from 0 to 1 is 1 CPU cycle. 0 to 2 is 2 CPU cycles. Okay. Now, using the first come, first serve algorithm with an arrival sequence of A, B, so assuming the jobs arrived in the order of A, B, C. A came first, B came next, and C came last. The timeline of the CPU will be like this. So at time 0, job A is the first one that came. Therefore, A is executed first. And because it's a first come, first serve, it is non-preemptive. That means A will complete its execution, all the 15 cycles. So time 0, 1, 2, 3, 4, 5, up to 15, the CPU will be executing job A. Excuse me. At time 15, A is complete. So job B will be swapped into the CPU. B has a CPU cycle of 2. So 15, 16, 17. Job B has completed its execution. Job C is given to the CPU at time 17. Job C has only 1 CPU cycle. Therefore, from 17 to the 18th CPU cycle, job C is also complete. Now, what is the average turnaround time? That is, it took the CPU 15 milliseconds or 15 CPU cycles. Then from 15, job B is, it's completed on the 17th CPU cycle. Then job C completed on the 18th CPU cycle. So you strike the average, 15 plus 17 plus 18, all divided by 3. That should give you 16.67 milliseconds. That is the CPU cycle for this first come, first serve algorithm with these jobs in consideration. Now, will it matter when the order of the arrival of these processes are changed? Here in our previous scenario, A came first, B followed, and C. We are going to look at the situation where C comes first, B comes next, and A comes last. Let's look at this. From time 0 to time 1, C is executed. C has only 1 CPU cycle. B has 2, so from 1 to 3. Then A has 15, so 3 to 18. Now, what will be the average turnaround time? You get 1 plus 3 plus 18. Okay, that will give you 22 by 3. 22 by 3 gives you 7.3. So you realize here that even though we are using the same first come, first serve algorithm, the order of arrangement of these jobs is really, really important. That means that here you have a maximized response time compared to the first order. That is why this type of algorithm is suitable for the batch job. So in the batch job, you take your time and arrange the jobs in a way that will be, that will use the CPU in an efficient manner. Okay, so I hope this is clear.
Yes, sir.
Very good. So this is the drawback that actually prevented the use of this first come, first serve algorithm. A lot of people are not using this algorithm because of this drawback. Then comes the next algorithm, that is the shortest job next. Okay, this is also a non-preemptive scheduling algorithm, also known as the shortest job first. Okay, this is the shortest job next, also called as the shortest job first. This handles jobs based on the length of their CPU cycle time. Okay, here the jobs that have short CPU cycles are given higher priority, or they are executed first. Why? We don't want the person to stay in the queue for a longer time. So is there anyone who is buying only one pack? The person comes from the back. Me, I'm buying one pack. The person will come, we will serve the person. After the person goes, we'll call. Is there anyone who has only one pack? Another person can, yes, me. We serve that person again. After him, and then we ask, anyone with one pack? Nobody comes. Then it's okay, anyone with two packs? Those with two packs will come. We want to serve those with little, burden as much as possible than those who are going to buy 15 packs. They will wait so that later, when everyone is gone, they will get time for them. It is non-preemptive scheduling. It means that when a job starts its execution, it will complete before it's taken out of the CPU. This type of algorithm is well suited for environments where the estimated CPU time required to run each job is given in advance. If we don't know the estimated CPU cycle for the jobs in question, we cannot use this shortest job next algorithm. Okay, this is also applicable to the batch jobs, because before we give a batch to the CPU to execute, we have arranged all of them and we know how much time each one is going to take. It does not work in an interactive system, all right, because response time is minimal. This is because users don't estimate in advance the CPU time that is required to run their jobs. Okay, so let's look at these 4 jobs here. We have jobs A, B, C, and D with their CPU cycles 5, 2, and 4 respectively. Now, if we use this shortest job next algorithm, this is what will happen. At time 0, operating system will ask, which of these jobs has the shortest CPU cycle? From this diagram, we see that it is job B. B has only 2 CPU cycles. So the CPU will start executing job B. Job B executes from time 0, time 1, time 2. Job B is completed because it's non-preemptive. Then operating system will go again and ask, who has the shortest CPU cycle? B is gone. Now we have D, who has 4 CPU cycles. So operating system will execute job D. So from 2, we go to 3, 4, 5, and 6. 4 CPU cycles. D is completed. Operating system will ask again, who has the shortest job next? We look at this, see if D is gone, we have process A, who has 5 CPU cycles. So A is given the mantle to execute. A execute for 5 times, and we get to 11. Prince Miller, your hand is up.
Yes, sir. Sir, please, I have a question. So
Go
please, during this cycling, even if there is an even if there is an immediate job, that emergency job, as you said, that one will still come and occupy, will still come and take the required CPU time, which will affect the next job on the line. Oh,
Yes, yes, exactly. Here we
okay.
don't consider jobs with priorities. We don't consider emergency jobs. It's like you going to a hospital where they say whether you are in an ambulance or you are dying, when you come, you have to join the queue because it is a non-preemptive job. In an emergency situation, when you are in the consulting room with the doctor and an emergency, an ambulance comes in, you will be taken away from the doctor's consulting room. So that is preemption. You will be preempted, right? That is the only time the emergency job can be brought in. But in this, it is a non-preemptive. And so once the doctor is attending to you, the whoever, whether it's emergency, dying or drowning, the doctor will not attend to them. So, right, the only time or the only thing we can do is that when an emergency comes in, when an ambulance comes in, we give that ambulance the shortest, allowable time, maybe so that when the CPU, when the doctor finishes attending to you, the emergency situation will have the shortest job or the shortest CPU cycle, and then that's the only time the doctor can attend to. Otherwise, it is not allowed. I hope that is clear.
Yes, sir. Thank you very much.
You're welcome. All right, so at time 11, C is the only job that is now in the system, and it has 6 CPU cycles. So 6 from 11, we give 6 CPU cycles to C, and we get to 17. What will be the average turnaround time? We have 2 plus 6 plus 11 plus 17 divided by 4. That gives us 9.0. So if you look at this algorithm, the average turnaround time for these 4 jobs is 9.0. Okay. So here, can we say this one is optimal or is better than the previous one that we have looked at? Here, the average turnaround time following the first come, first serve in the first order was 16.67. Now we have 9.0. Okay. Now let's look closely. I hope this will, or let's hope this will give us a consistent minimum average if the order is reversed or if the order of the arrival of the jobs are changed. Now look at this. 5, 2, 6, 4. Jobs B will be executed first, D, A, and C following the same order. Okay, now you're going to find a formula to calculate the average turnaround time. Here we have 2. What is 2? 2 is the number of CPU cycles the job B2 plus 4 plus 2. What is 4 plus 2? That is the first job was 2. So that is fine, job B. Job D has CPU cycle of 4. And this CPU cycle was executed after the first job has been executed. The first job took 2. So the next one is 4. That is 4 of the D, sorry, 4 of the D plus the 2 that has already been used by the B. So 4 plus 2. Okay, so let me just write them on top. This is for B. This is for D. Then we have that of the next job, A, which is having a CPU cycle of 5. But A was executed after D, which was 4 plus 2. Okay, so you have 5 plus 4 plus 2. This is for A. Then the next job was job C, which has 6 CPU cycles, which was executed after A and D and B were executed. So this is our C. If we put all together, divided by the number of jobs, 4, you still get the 9.0 that was gotten here. All right. All right. Now let's move on. So what can we say? We can say that 4 times 2. What is the 4 times 2? Are you getting this?
8.
Yes. So 4 times 2. No. I'm just asking, where did we get this 4 times 2?
From the
Yeah.
end.
We are trying to find a formula that we can use to calculate the average turnaround time. So now follow closely and tell me where the 4 by 2 came in.
Yeah, sir, please. The 4 by 2, we got it from the 4 represents the number of jobs given.
Okay.
And the 2 also represent that's the CPU cycle, the list, which is B2.
Okay.
Yeah. So with this one, I think we will take the number of jobs given, then we multiply it by the lowest, then we add it to the same number of jobs given, but this time we subtract it by 1, and we add it to the next number after the lowest.
Okay.
We do it until we are able to get the whole table.
Guys, are you with him? Do you understand?
Please no.
Please.
No, sir. No, sir.
Please explain again.
No, sir.
No,
Okay,
he
so
has added too much.
okay, sorry. So what Sir is trying to say over here is when we take the job and the CPU cycle, the jobs over there we have A, B, C, D, which is 4. So first of all, we write our 4. Then we now multiply it with the lowest CPU cycle, which is B2. That is 2. So we have 4 times 2 plus, now the next one is 3. So that means in the job list given, we had 4, but this time we are going to subtract 1 from the 4, making it 3 because already we've input the CPU cycle for B, which is 2. So now automatically it's assumed we are left with 3 jobs to go, which is A, C, and D. So now since we have A, C, and D, which is 3, we now write 3, and now we multiply it by the lowest number, which is 4. When we are done with that one, then we come and add. So this time around, our jobs, we are left with 2, which is A and C. So we write C, and we also multiply it by the lowest CPU cycle. Then we add it to the last cycle which is left, which is C. So now the job automatically becomes 1. So now we have 1 times 6. That is how we got the equation there.
Yeah, understandable.
Yeah,
Understandable?
Yes,
Okay.
sir. Yes, sir.
Yes,
Yes,
sir.
sir.
All right. Thank you. Thank you. Please give me your index number.
Okay, sir.
Yes, please go ahead.
Say 040
040
919
919
140.
140. Okay. All right. Thank you.
Thank you,
Okay,
sir.
guys, let me make it even more clearer. Now, as you can see from the above here, as you can see from this equation here, the time for the first job appears in the equation 4 times. What is the time for the first job? That is the 2 here. It appeared 1, 2, 3, and 4. Are you all with me? That is why we have the 4 times 2. Right? Now, similarly, the time for the second job appeared 3 times. What is the second job? 4. This is 1, 2, and 3. So you have 3 by 4. Then the time for the third job appeared twice. The third job is A, which is 6. No, is it, sorry, which is 5. 5 appeared 1, 2. That is why we have 2 by 5. And then the time for the last job, that is job C, 6, appeared once, which is this one here. That is why you have 1 by 6. I hope this is even making it more clearer.
Yes, sir.
Very
Yes,
good.
sir.
Yes, sir.
Okay, so now with this
Yes, sir.
understanding, let's deduce a formula. So you have the time for the first job appearing n times. What is n times? We have 4 jobs, and the time for the first job appeared 4 times. So that is T of n, right? T1, that is the first job, T1n. So that's what you have here, T1 of n, plus the time for the second job appeared 3 times, that is n minus 1, plus the time for the third job appeared n minus 2 times, plus, so you get all that up to the time you get the time for the nth job appearing n by 1 time, all divided by n, which is the total number of jobs there are. I hope that is clear.
Yes, sir.
Yes, sir.
Very good. So with this, we have deduced a formula that will be used to calculate the average turnaround time for the jobs in the shortest job next and that of the previous one, that is the first come, first serve. However, the shortest job next algorithm is optimal only when all the jobs are available at the same time and the CPU estimates these, the times correctly. You understand? Now, with that, let's look at the priority scheduling, or an Indian man will say priority. Okay. Now, this is a non-preemptive algorithm. This is the third algorithm that is non-preemptive. If you looked at the first two, first come, first serve, the shortest job next, and now the priority scheduling algorithm. This algorithm gives preferential treatment to important jobs. The priority determines the importance. This algorithm, mostly common in the batch system, allows the programs with the highest priority to be processed first. This will be uninterrupted, okay, until their CPU cycles are completed or until they execute a natural way. That means they want to perform an IO operation. This is actually uninterrupted, not interrupted. Okay? Uninterrupted. Now, in this, we are worried about the jobs that have equal priorities. So if 2 ambulances arrive at the same time, or if there are 2 ambulances, what will happen? In that case, the first come, first serve is used. So the ambulance that arrived first will be taken care of. We are talking about jobs that have equal priorities. Both are accident victims, and ambulance A came before ambulance B. Therefore, ambulance A will be given priority over ambulance B because it came first. Okay, so these priorities can be assigned by a system administrator using characteristics intrinsic to the jobs. So looking at the jobs and their importance, the priorities are assigned by the system administrator. Now, even though we are not using, we don't know which of these scheduling algorithms our operating systems are using, but we can change the priority of some of the processes that are running on our computer systems, even now as we speak. I am using Windows 10. I'm going to change the screen and show you something briefly. So Let me change the sharing of my screen. Please hold. Take you to the task manager. Now, this is Windows 10. If you have Windows 10, you can go to the task manager. I'm sure it's similar to the other Windows operating system. Those who are using the Linux and the Unix, look for a way to get your task manager. Now here, if I go to the detail, I hope you can all see my task manager, please.
Yes, sir.
Great. If I go to the details tab, I will see all the tasks or the jobs that are running in my computer system. So you can see I have application frame, host, T whatever, audio DB, calculator, Chrome. This is how many tabs I have opened, then code, then con host, and all these are processes or jobs that are running in my computer system. If you look at their status, they are running. And then they have their process IDs. Remember last week when we were forking some of the processes in the Unix environment, we're talking about their process ID. So each process has a process ID. Now, when I right click on any of these processes, the menu that comes, there is one that I can use to set the priority. Okay, so these are the priorities. We have the real time, the high, above normal, normal, below normal, and low. Okay, so presently, my calculator is running with the priority as normal. I could use these to change the priority of my calculator. So this is the priority scheduling we are talking about. These priorities can be assigned by the system administrator using characteristics intrinsic to the jobs. These jobs, okay, so I'm going to change the sharing if there are no questions here. All right. These jobs are usually linked to one of the several ready queues by the job scheduler based on their priority, so that the process scheduler manages multiple queues. So here, as we looked at my task manager, we saw about 6 different priorities. So in the computer system, these priorities are going to be queued. So you have the first one, the above normal, the normal, and all that. So you have 6 queues. Then the operating system, sorry, the process scheduler will manage these, what do you call the jobs from these. So maybe it will take 2 from the highest priority, then it will take 1, depending on how it has been programmed. So this is the priority scheduling. I hope it is clear, please.
Yes, sir.
Yes, sir.
And it's also quite straightforward. Now, these priorities can be determined by the processor manager based on the following criteria. 1, the memory requirement. There may be a queue for processes that require more memory or large memory, and then those that require small or less memory. Number 2, the number and type of peripheral devices. There will be a queue for processes that require higher peripheral device or more peripheral devices. This guy wants to access the keyboard, he wants to access the mouse, he wants to access the USB, he wants to access the Bluetooth, he wants to access the camera. So a lot of peripheral devices are going to be used by this process. So let's give it a higher priority or a lower priority, depending on the designer of the operating system. Also, the total CPU time. How much CPU cycles does a process need in order to complete its task? Based on that, the task can also be given a priority number, whether it's a low or high. And lastly, the amount of time that has already been spent. Okay, so has the process started its execution? How much time does it need to complete? Maybe if he needs more time, like Dantimuni Wache, if the guy is buying 7 parts and already has been given 4 parts, why do we keep him waiting? Just remaining 3. So okay, let's just let him finish. Or the guy has been given 4 let him wait so that others who have not been served can also be served. So all these are different ways that the designer of the operating system determines to assign the priorities. And remember, it was said that whether the algorithm is going to be used or not is dependent on the designer of the operating system. He decides which of those policies are important and they choose them. So this is called the aging. When you look at the amount of time a process has already spent in the computer system. We'll talk about this aging concept later in this course. All right, if there are no questions, let's go on. We go to the shortest remaining time algorithm, the SRT. This is the cousin of the shortest job next. It's a cousin of the shortest job next. Here, it is a preemptive algorithm. So this is the first preemptive algorithm we are looking at. Okay. Here, the CPU is allocated to the job that is closest to its completion. We have given this guy all this while to complete. Why are we stopping him when it's just about a day to completion? Because he has just small amount of time to complete. Let's give it to him. So every time the CPU interrupts, so every time the process scheduler interrupts, the operating system will calculate how much time is left for all the jobs. And it will select the job that has the least remaining time. Okay. Even while the job with the least remaining time is being executed, if a new one is brought to the system, to the ready queue, that appears to have a shorter time, then that job will be preempted. Okay. Now, can we have this job in an interactive system? Who can tell me? Can this algorithm be implemented in an interactive system? Hey, so.
Yes, sir.
Yes, sir. Now can. Say myself, yes, sir. You want to? Do you want to explain? Or I should explain?
Explain. Say, if in an interactive system, let's say there is already a job in process, and then there is, let me use a printer command as an, okay, there's an IO input.
Okay.
That one, which will be preempted to run before the other process also continue.
Okay. All right. Okay. Thank you. Thank you. Have I taken your index number today?
No, sir.
Okay. Do you want me to take your index number?
Yes.
Okay. Please give me your index number. 0
040
919
671.
671. Okay. All right. Thank you for that contribution. Let me come again.
I told him to say.
Want to say something?
No, I said I told him to say.
You taught him what to say. Okay, then when I give him the marks, he'll give you some. All right. Okay. So let me break it down. So in an interactive system, you know that the jobs arrive in an uninformed manner. It can come in any time. Okay, and you realize that the time that the job will last, or the CPU cycle of a job, is not known in advance in an interactive system. And therefore, we cannot implement the shortest remaining time, because here the operating system has to take into consideration the CPU cycle times of all the jobs in advance before this algorithm is used. But we don't have that laxity in an interactive system. So the answer is no, because it requires advanced knowledge of the CPU time for each job. And we don't have that in the interactive system. Now, when I ask you this question, for example, in an examination, and I give 10 marks, or if I assign 5 marks to this question, I am not expecting you to go and write this short statement here and expect to get 10 marks. Some of you have been doing that. Some of you have been doing that. You get the answer correct, but I can't give you full marks. So if you give me something like this, instead of 10, I'll give you 2 marks. Then you call me next semester and tell me that, say, as for the questions, I answered power, but I got low mark. Please, when I give you questions, look for the marks that are allotted to the question and answer accordingly. I have always been saying this in my class, but some of you just turn deaf ears. So when I'm marking, I'm tempted to think that people don't like marks. Anyway, that is just by the way. Now, this algorithm incurs more overhead than the shortest job next because the operating system has to frequently monitor the CPU time for all the jobs in the ready queue. There's too much trouble for the operating system. At every CPU cycle or at every interrupt, this operating system has to calculate all the jobs in the ready queue. It has to calculate their remaining time. And it's an overhead. It's a lot of work for the CPU. Okay. Are you with me?
Yes, sir.
Yes, sir.
Now, with that, let's see if we can look at the what do you call it? The average turnaround time here. So to illustrate the shortest remaining time algorithm, let's consider these 4 jobs. Jobs A, B, C, and D with CPU cycles 6, 3, 1, and 4 respectively. These arrived at the following times. So job A arrived at time 0, B at time 1, C at time 2, and D at time 3. So if we're talking about seconds, first second A arrived, the next second B came, next second D came, C in that order. Okay. Here, job A, so at time 0, all these job 0 was, at time 0, job A was the only job in the CPU, in the ready queue. Therefore, we give job A to the CPU to execute. At time 1, job B arrives. So what happens? The operating system has to calculate the CPU cycles of A and B to see which one has the least. So at time 1, A has executed 1. So A has 5 now, and B is coming in first, so it has 3. So 5 and 3, who has the shortest remaining time? Job B. So B is given to the CPU to execute. Job B executes 1 CPU cycle, and at time 2, job C arrives. C has 2. C has 1 CPU cycle. So at that time, let's calculate. Job B has executed 1, so it's left with 2. B still has 5. Sorry, A still has 5. B has executed 1, so it has 2. C arrives, it has 1. So now we have 1, 2, and 5. 1 is the least or the shortest. So the CPU is given to job C. Job C executes 1. Then job D arrives. So at that time, job C has executed 1 and it has only 1 CPU cycle. Therefore, the remaining time for job C is 0. D has come in. D has 4. So now we have 5, 2, 0, and 4. Which one is the least? Job B, which now has 2. So B is again given the chance to execute. B executes next. So 1 CPU cycle here at time 4. The operating system will interrupt again. We do the calculation. Now B has executed 1. So now it has 1. Okay. So let's look at the time. Now we have 4, 1, and 5. Okay, B has executed, so now this B is not there. This one is also gone. So now we have the D, which has 4, B, which is now 1, and A, which has 5. So B is still the least. So B is given the chance to execute. At time 5, the CPU interrupts. Now B has executed 1, it is left with 0. Okay, that means that now B is taken out of the equation. Now we have processes D and A. D has 4, it has never executed. A has 5. Okay, so D has the smallest. So D is given the CPU time. D is executed at time 6. CPU comes in, D now has 3, which is still smaller than 5. So D will continue. D will have 2 now, which is still less than 5. D will continue. Now it has 1, which is still less than 5. Then D becomes 0, which is still less. So process D is executed all throughout. Then at time 9, we have D is also now 0. So it's now out of the system. So we have only process A, which has 5 CPU cycles. So A will start here at time 10. A is now 4, but there's no other job. So B continues to execute all until it gets to time 14. Please, I'm sure this is clear. The timeline is clear.
Yes, sir.
Very good. Now, if the timeline is
Okay,
clear,
so please,
come again.
so that means the
I should go over.
CPU with the highest number will execute last.
The job with the highest number will be executed last. Okay, so Benjamin and Orleans, you have your hands up. Is it that you want me to go over?
So I wanted to ask a question.
Okay, please go ahead.
So I wanted to ask about the arrival time. Is it the interval? Is it always like 1, like from 0 you go to 1, or can there be a situation where from 0 you skip 1 and go to 2 or something like that?
Okay, so here we are talking about the time they arrived. Okay, so the first second A arrived, then the next second B arrived, the next second C arrived, the next second D arrived. So there can be the situation where A arrived at time 0, no process arrived at time 1, but let's say B arrived at time 4. You understand? So that is a scenario we are creating. But in this case, the jobs were arriving at every second. So first, second, third, second, third second, fourth second, and fifth second. Orleans, is that clear?
Yes, sir. Very clear.
Okay,
thank
good.
you.
Sure, you're welcome. Benjamin.
Sir.
Yes.
Okay, so I want to add to the explanation, like my opinion.
Okay.
I want to use both app and then the both drivers as an example here.
Okay, please go ahead.
As in a reference to what? Yeah, let's say we have both driver A around GTUC campus, main campus, and then we have another around Abeka campus at a police depot, and you want to order a boat. Okay. The web pages will actually go for the shortest distance. In other words, that's what they use for the web, the indenting of web pages or apps like that.
Okay.
So let's say the car around will actually pick up has the shortest before ordering than the boat drivers, and then the car's an example. The one closer to you is the one that you have or you get at the end of your order, instead of getting someone who is far away from you.
Oh, okay.
Yes.
Oh, okay.
Yes.
Oh, oh, Benjamin.
The network.
Benjamin. Oh,
Sir, we can't hear you.
Says Vodafone. Vodafone.
And
the
your
moment is-
crowd,
The
and your
processor
crowd.
is in a
oh, Benji.
which is lesser than executed first before the processor 2.
Okay. Okay, Benji.
Hello.
Oh, it's quite unfortunate. Your line was breaking along the line, but
Oh.
your example is quite interesting. So you are trying to summarize. I mean, to summarize what you're saying, this algorithm is followed by the Bolt organization, right? When you order a cab, it uses an algorithm that is similar to what we are discussing here in the selection of a driver for the client, right? I wish your network was quite, better than it is. So you'll give us more explanation. So give yourself some time, maybe getting
Yes,
to give yourself some time, maybe getting to the end of the class. Excuse me, guys. Maybe getting to the end of the class. If your network is better, perhaps you can come in and finish off with your demonstration. It's interesting. We want to get to the bottom of it. All right. So let me take some time to retake this scheduling algorithm as was requested by some of you. Let me clear the screen. Olin, your hand is up. Or is it a mistake?
Yes, sir.
Okay, please go ahead. Olin, if you are speaking, we cannot hear you. Okay, let's assume his network is also not in favor today. But guys, I hope when I speak, you can hear me clearly.
Yes, sir.
Yes, sir. Crystal.
All right, very good. Okay, so let me illustrate this again. We have these 4 jobs, A, B, C, and D. Their CPU cycles are 6, 3, 1, and 4, respectively. I hope that one is clear. Now, on the arrival time, this is the order they arrived in the ready queue. First was job A. Then the next second, job B came. Then the following second, job C came. Then the next second, job D came. So that is their arrival time, time 0, 1, 2, 3. And here we are also assuming that the interrupt, the operating system or the process scheduler interrupts every second. So every time this process scheduler interrupts, there is a new job added. So at time 1, at time 0, the process scheduler interrupts and there is only one job. At time 1, the process scheduler interrupts and there is AB. At time 2, the process scheduler interrupts and there is ABC. At time 3, the process scheduler interrupts and there is ABCD. So we are assuming that after that, every time, so at time 4, when the process scheduler interrupts, there is still jobs A, B, C, D. At time 5, when the process scheduler interrupts, there's still job A, B, C, D. So that is what the arrival time actually indicates. So now coming to the timeline, at time 0, when the process scheduler interrupts, there is only job A. Okay, so the operating system or the CPU is given to job A to execute. At time 1, when the process manager or scheduler interrupts, job B has been added. So now we have jobs A and B. This is the shortest time remaining algorithm. So the operating system has to calculate and determine which job is given to the CPU. So here, job A has executed one CPU cycle. Therefore, job A has only 5. It was having 6 in total. Now it has executed 1. So now job A has 5. Job B has 3 because it is new in the system. So the operating system will calculate or will determine between 5 and 3 which one is the shortest. 3 is the shortest. So job B is given to the CPU to execute at time 1 here. Then at time 2, the process scheduler again interrupts. Now at time 2 also, process C has come into the scene. So now there are A, B, C, these jobs 3 are now in the ready queue. So the operating system has to calculate which job has the shortest remaining time. Now job B has executed 1, so it is left with time 2. Okay, now C joins. C has only 1. So now we have 1, 2, and 5. Okay, operating system determines that 1 is the least. Therefore, job C is giving the CPU to execute. So C will execute its 1. Then the next minute, the next second, when the process scheduler interrupts, job D has been added. So now we have A, B, C, D. A has 5 CPU cycles, B has 2 CPU cycles, C has executed 1, so now it has 0 CPU cycles. Okay, that means it is finished, so it's taken out of the system. And then job D has joined with 4 CPU cycles. So now the operating system will determine among 5, 2, and 4, which one is the least. You realize that 2 is the least, which is job B. So job B is giving the CPU to execute. At time 4, the process scheduler or again interrupts. This time, no job has been added. We still have, C has completed its execution. So we still have jobs A, B, and D. Now, B has again executed 1. So B has time of 1. So the operating system will determine amongst 1, B now has 1 and job D has 4. So amongst 1, so let me cancel this. Amongst 1, 5, and 4, which one is the least? 1. Therefore, B is given the chance to continue to execute. So B executes from 4 to 5. At time 5, the process scheduler again interrupts. B has only 1. B is giving them, no, here B has executed and so it is 0. So now B is done with. We have 2 processes or 2 jobs, jobs A and D. A has remaining CPU cycle of 5 and D has remaining CPU cycle of 4 because D has not executed. So among 4 and 5, which one is the shortest? 4, which is D. So at time 5, D executes. At time 6, the process scheduler interrupts. Now D has executed 1, it is left with 4. 4 is still smaller or shorter than 5. So D continues to execute. Here it's now left with 3. 3 is still smaller than 5. So D continues to execute. Now it's left with 2, 1 up to the time it gets to 0. When it gets to 0, now D is taken out of the system. There's only A in the ready queue. So A is given to the CPU. A now has 5 CPU cycles. So A will execute from 5, 4, 3, 2, 1, and 0. And A also finishes its execution. Please, is it okay now?
Yes, sir.
Yes, sir.
Yes, sir. Sir, please, a question.
Yeah, please go ahead.
Yes, sir.
Yeah, sir, please, can I say that the arrival time determines the number of CPU cycles to be executed?
No, please. The arrival time determines the time that the process or the time that the job arrived in the ready queue.
Okay.
And then the CPU time can be likened to the age. Assuming we take this class, I started the class at 9 o'clock. At 9 o'clock, you entered. Then 9:05, another person entered. 9:10, another person entered. So the times they entered the class is the arrival time. The CPU cycle is, let's assume your age. Your age will be different from your arrival time. All right. Ollins, your hand is up again.
Yes, I wanted to ask a question, but my network was messing up.
Yes, please go ahead now.
Okay, sir. So if I'm understanding this right, then let's say the arrival time at 0, A came in with a CPU cycle of 6, and
yes,
the next arrival time, which is 1, there was no job to be executed. So let's say job B came in at arrival time 2 with a CPU cycle of 4. In that case, that means job A has executed 1 in the 0 slot and has executed another one in the 1 slot. So that means A is left with 4, and now B has come in with a CPU cycle of 4. So in that case, is it going to apply the first come first serve because they now have equal CPU cycle?
Yes, that is a very good question. I'm assuming that in this case, then there will be the first come first serve policy.
Yes, sir.
Yes, that's a very good question. Thank you.
Thank you, sir.
All right. Now, in this case, the turnaround time here is a little different from the previous algorithms that we've looked at. The turnaround time is the completion time of each job minus its arrival time. Okay, so if you look at A, what will be the turnaround time for A? That is the completion time of A minus its arrival time. The completion time of A is 14 here, right? And its arrival time is 0. So 14 minus 0 is 14. Okay. That of B is what? B completed at time 2. B arrived at time 1. So 2 minus 1 is, no, sorry.
1.
No, B ended at 5. I'm sorry. B ended at 5. And its arrival time is 4. Sorry, it's 1. I'm sorry. Okay. So you have 5 minus 1 giving us 4. Then that of C. C completed at time 3. Okay. And its arrival time was 2. So the turnaround time for C will be 3 minus 2. That is 1. Job D completed at time 9. And its arrival time is 5. So the turnaround time will be 9 minus 5. That is 6.
So this is supposed to be 4.
Sorry, D completed at 9, time 9. Okay, and it arrived at 5. 9 minus 5 is 4, right?
Yes, sir.
Okay, I think there is an error here. So the turnaround time for D is actually 4, not 6. I'm sorry. Okay. So I think there was since there's an error here, we will definitely get an error. So the average turnaround time will be the turnaround time for each of these jobs divided by the total number of jobs. So here we have 4. The average turnaround time will be 14 plus 4 plus 1 plus 4. So 4 plus 1 will give us 5 plus 4 will give us 9 plus 9, sorry, plus 14 will give us 23. So you actually get 23 over 4. What is 23 over 4? 18, 24, 6. Okay, so it's actually about a little lower than this one here.
5.75.
Yes, 5.75, a little lower. Okay, thank you. So the average turnaround time will be 5.75. This is actually 4, not 6. All right. So this is how you calculate the average turnaround time using the shortest job next. Now, there is an assignment here. How does the same job compare to the same problem using the cousin, the shortest job next policy? All right, so you're going to calculate the turnaround time for this job using the shortest job next, and then compare. So calculate the turnaround for each job, find the average turnaround, how faster is the shortest remaining time than the shortest job next. So this is an example, sorry, this is an assignment. You have to work on this and submit in the portal. I'll create the submission in the portal where you can upload your work. The deadline will be coming Sunday, 12 a.m. Okay, no, 11:59 p.m. Sunday, 11:59, 2300. And I didn't gonna make it again. The deadline is Sunday, 23 hours. Sunday anajo, and it will be 23 hours, 59 minutes. Yes.
Make it on Monday.
Put it somewhere. Never me time.
We have another assignment to.
If I'm home, Papa Bay. If I'm home, Bay. Now let's go to the next one.
Yes.
I got one assignment. I'll do another assignment. Sika na mde ma se fashion bottom and kavaka se sika show bottom je wonye me de no.
I don't know.
Me mwana. All right.
Credit card.
I have very
deadline.
You. All right. So let's go to the next algorithm if there are no questions. Can we? All right, good. I'm assuming that is a yes. So that the next one is
hello,
the
sir.
okay.
Hello,
The
sir.
next, yes, please.
Hello, please. In a case where we are being asked a question concerning this, are we supposed to illustrate all the diagrams provided in answering the questions?
You do that as best as you can. In as much as I know you have the answer, I want to see that you understand the processes that are involved. You understand? So you try as much as possible to explain yourself. You may not be able to get it all correct, like I have in my slide here, but try to explain the processes as you move along. Is that okay?
Thank you, sir. Meaning errors are accepted, sir.
Yes, definitely. Even the operating system accepts errors. That's why there's an error handler. So that is fine.
Thank you very much, sir.
You're welcome, sir. All right. So with that, let's go to the round robin. This is also a preemptive scheduling algorithm. This is the second preemptive algorithm we are looking at. This is used extensively in an interactive system. This is based on a predetermined slice of time that is given to each job to ensure that the CPU is equally shared. I'm underlining the equally shared. So the CPU is equally shared among all the active processes, and it is not monopolized by any one job. So here, there is what we call the time quantum. Okay, the time, the CPU time. Shatawale, kindly mute your mic. Amwako, thank you. All right, so here, the CPU time is divided into a time slice referred to as the time quantum. This time quantum can vary from 100 milliseconds to 2 seconds. So can be 1 second, can be every 2 seconds, can be every 1 second, or 100 milliseconds. What is 1 second over a million? Okay, so anytime within this time quantum, the operating system is set to interrupt. Okay, every time it interrupts, a new job is brought to the CPU. So all the jobs are placed in the ready queue using the first come, first serve. The first job is selected from the front of the queue sets the timer to the time quantum, and the CPU is allocated to this job. When the time quantum expires, if the job is not completed, if the job is not finished, the job is preempted and put at the end of the ready queue. And then the next job is given to the CPU. So if it is every 2 seconds, the first job is taken. After 2 seconds, whether it has completed or not, it is removed. If it is complete, fine. If it's not complete, it is taken to the back of the queue. Then the next person comes in. So when you go to the anti-muni wache, everybody is given one wache. You buy one. If you are not done, you go and join the end of the queue. The next person comes. If he's buying only one, lucky him. He buys it and he goes. The next person comes. So everyone is given an equal opportunity to execute on the CPU. This is called the round robin algorithm, and it is suitable for the interactive system. This is what I have always been talking about. Okay, when I say that the CPU is divided over time and each one is given a slot on the CPU. Okay, if a job's CPU cycle is shorter than the time quantum, assuming a job is going to be executed in less than 1 second, assuming the time quantum is 1 second, then one of these two actions will be taken. If this job, if it is the last cycle, if it is the last CPU cycle of the job and the job is finished, then all resources that are allocated to the job are released and the job is returned to the user, means it is done with. If the CPU cycle has been interrupted by an IO request, then information about the job is saved in its PCB and it is linked to the end of the appropriate IO queue. Later, when the job is completed with the IO, it is returned to the end of the ready queue to await its allocation on the CPU. So if the CPU comes and you are done, fine. If not, you are taken to the end of the queue. If you are waiting for an IO, you are removed and sent to the IO queue. When you are done, again, you'll be brought to the end of the ready queue. Just as simple as that. So looking at these jobs, A, B, C, and D, with CPU cycles 8, 4, 9, 5 respectively, if you look at the normal arrival time, 0, 1, 2, 3. Okay, so the turnaround time, so here is just simple. A is giving, so here we are assuming that the time slice or the time quantum is 4 milliseconds. 4 milliseconds. So it's first come, first serve. A is giving the CPU at 4 milliseconds. A is taken away. Job B is brought in. So what do you call it? A had 4 CPU cycles. It has executed 4. So now it will be left with 4. B is brought in. B is executed 4. Now it is left with 0. C is given. C has 9. So it will be left with 5. Right? D is brought in, D has 5, it will be left with 1. A now has 1. Sorry, A has 4, so it will be executed. A is now having 0, it's taken out of the system. B is done with, B is complete. So next one is C. C has 5, it will be executed 4, now it will be left with 1. D is given, D has only 1, so it will execute 1, and then it will be left with 0. D is done with. C has only 1 now, so C also is given and it's completed here. So C is done, D is done, A is done. What will be the average turnaround time? That is the completion time minus the turnaround time for each of these jobs is the completion time minus the arrival time. So what do we get? The completion time of A is, A started here, A completed at time 20. So 20 minus 0 is 20. That of B, B completed here, 8. So 8 minus 4 is, yeah. Where is B? Oh, B. The completion time of B is 8. 8 minus 4 is 4. I think there's an error here too. What is going on? It's unfortunate. Okay, C completed at 26. The arrival time of the C was 8. 8, right? So 26 minus 8 is 18. This one too is 24. I think I interchanged the positions of B and C. I don't know. And that of D is 25 minus 12.
Okay.
25 minus 12 should give us 13. This is also 22. Okay. I think there was a mistake when I was doing this. All right. Sorry. So what will be the average turnaround time? You get this plus that plus this plus that divided by 4 should give us the average turnaround time. Considering the fact that these values are incorrect, the average turnaround time is flawed. Okay, I'm sure we'll get something smaller or shorter than this. All right, so 2 hands are raised. Michael. If Michael is not available, Prince, please go
I
ahead.
forgot to lower my hand.
Oh, okay, that's fine. Prince.
Yes, sir.
Yes, please go ahead.
Sir, please read the B. The arrival time is the one at the top there.
Okay. Okay, the arrival time. Yeah. Okay, this is the round robin. So if you follow that, we will get it wrong. Okay, so the B. Yes. Okay, so the average turnaround time of the B will be 8 minus 1. That is 7. Okay, so that is correct. Thank you. Thank you, Prince. And then that of the C will be 26 minus 2. That is 24. Okay, correct. Then that of D will be D completed at 16. So no, 25. So it's 25 minus 3. That will give us 22. Oh, okay, Prince. Thank you. Okay, guys, on that note, I guess our calculation is correct. So we have 18.25 as the average turnaround time. All right, Prince. Prince, give me your index number, please.
040
040
919
919
780
040 919 780, right?
Yes, sir.
All right, thank you.
Okay.
All right, guys, so there we have it. That is the average turnaround time using the round robin. The efficiency of the round robin depends on the size of the time quantum in relation to the average CPU cycle. If the quantum is too large, okay, that is, if the CPU, if it's larger than most of the CPU cycles, then the algorithm will reduce the first come, first serve scheme. If the quantum is too small, then the amount of the context switching slows down the execution of the job. So here, what we are trying to say is that if the time quantum is too small, like here we have 4 milliseconds, assuming the time quantum is 1 millisecond, I mean, there will be too many context switching. A will come, B will come, C will come, D will go, all that will happen. And that will result in too many context switching. And remember, during the context switch time, the CPU performs no useful job, and that will reduce the efficiency of the computer system at large. Okay, if it is too large, then the algorithm reduces to the first come, first serve. If the time quantum is too large, then you are likely, or you are similarly executing the first come, first serve, because assuming the CPU cycle is 8, if A is giving the CPU, it will complete. If B is giving the CPU, it will complete. It's only C that will not complete, to be left with 1 CPU cycle. D is giving the CPU, it will complete. So if the time quantum is too large, you are simply implementing the first come, first serve under the guise of the round robin. I hope that is clear, please.
Yes, sir.
Very good. Lastly, the multiple level queue. This is not really a separate scheduling algorithm, but it works in conjunction with several of the schemes that we have discussed. It is found in systems with jobs that can be grouped according to a common characteristic. Maybe based on the characteristic, you use the priority based. So here you put them together. Okay, depending on the what do you call it? What the designer is looking for. Okay, the appropriate queue is selected. Okay, there can be a system that will gather all CPU bound jobs in one queue and then all IO bound jobs in another queue. Then the process scheduler will alternately select jobs from each of these queues to keep the system balanced. A third common example is one that is used in a hybrid environment that supports both the batch and the interactive jobs. In this case, the batch jobs are put in one queue, then the interactive jobs are put in another queue. The batch one is called the background, and the interactive ones are called the foreground. Okay, and then the operating system will use the algorithm that is appropriate, depending on whether the focus is on the execution of batch jobs or is on the execution of interactive jobs. Right, so here, it's not necessarily a unique algorithm, but it blends or it puts together a few of the algorithms that are suitable in the system. Some interesting questions if you are using the multi-level queue. Is the processor allocated to the jobs in the first queue until it is empty before moving to the next queue? Or does the processor travel from one queue to another queue until the last job on the last queue has been served? This is a question you want to ask yourself. Is it fair to those that have earned or paid for higher priority? There are some processes that have paid, like I went into my task manager to manually upgrade the priority of a process. If I do that and the operating system is using this multi-level queue, then there is no point in me doing it. Okay. Is it fair to those in a low priority queue? If the processor is allocated to the jobs on the first queue and it never empties out, at what point will it serve the others and the other queues? Can the jobs in the last queue get time off for good behavior? Maybe because they have stayed in the queue for a long time. Sometimes it's what I say. So is it also applicable in this multi-level queue? So these are some of the interesting questions or challenges that you want to address when you want to implement the multi-level queue. All right. So the answers depend on the policy used by the system to service the queues. There are 4 primary methods to the movement. 1, you can decide that you will not allow movement between queues. Once a process is given to one queue, it cannot go to another queue, can't move. Moving jobs from queue to queue, you can also decide that if a job has been in the queue for a long time because of the priority, maybe you move it to a different queue for it to be served. You can also decide to move jobs from queue to queue and increase the time quantum for lower queues. You can also give special treatment to jobs that have been in the system for a long time. That is the aging. That's what we'll talk about later. Okay. So these are some of the things that you have to actually consider when you want to implement the multi-level queue. All right, so this is a summary of all the algorithms and the advantages, their disadvantages, whether they are preemptive or non-preemptive, and what they are best for. I guess you can just read them to, summarize everything that we have talked about. Okay. In conclusion, the processor manager owes the CPU to all the system's users. So the CPU cannot be monopolized by one user. In this chapter, we've made the distinction between job scheduling, the selection of incoming jobs based on their characteristics, and process scheduling, the instant by instant allocation of the CPU using the time slice or the CPU timeline. Okay, if there are no further questions, I am ending the class here for today. Thank you all for coming. I'll see you next week. Don't forget to attempt the questions that are in the slide. Please go to the website and download the slide and use it. Answer the question.
Sir, please, what about the video?
Yes, I am recording and